Yes, I think we are live now. Hey, hi everyone. A very warm welcome to each one of you. I hope you all are healthy, happy, and safe from whichever the part of the world you are joining from. To give you all some quick context about DeFi, we are a global data science community that we started last year with the vision to democratize data science education. And in our constant endeavor for the same, we keep on conducting regular boot camps, live sessions, data challenges, and much more. Our today's session is one such initiative, and our heartfelt thanks to Serg for making it happen. I'm sure many of you would already know him, but for others, Serg is a seasoned industry professional who is currently working at Syngenta as the climate and agronomic data scientist. He's an entrepreneur and problem solver at heart, had co-founded a search engine startup in the past, and is truly passionate about using his ML skills to bridge the gap between the data and the decision making. Not just that, he's also an active community speaker, had delivered various talks at global conferences, and is also the author of the book titled Interpretable Machine Learning with Python. Now, without further ado, I'd like to bring him on and let him take over the session. Thank you, and over to you, Serg.
Hi, everyone. Thank you for that wonderful introduction. I hope everybody enjoys the session or at very least intrigued by this topic, as I am. I think there needs to be more discussion on this topic in our community of data scientists. Without further ado, I'll begin. There's a slide that's an introduction about myself, but it's done such a wonderful introduction that I don't think I can add too much to it. I wrote a book on the subject. My name is Serg Masís, and I've switched to data science after a long career in web development 4 years ago. Let's continue. I've broken up this session into two parts. The first one is what is XAI, Interpretable Machine Learning, in case you don't know, and what is fairness is followed by that. Before we begin on that part, there's also a practical part. That's, if you will, a third section, a third part, and it's basically going through a notebook. There are two ways of doing it. One is through Google Colab, which I highly recommend. You can just go to search.ai, DeFi 2021, and you'll get to it. I've shortened the URL. It's a very long one. The second one is through installing the GitHub in your local machine, making sure that it has all the libraries. That's a very long route. I don't recommend it unless you're hell-bent in running the example in your own computer. I do ask you that you go to the notebook and install the libraries, only the ones that are needed. Mind you, once you get there, there's two cells for libraries. The first one is only for those that are doing it through the desktop. If you're doing it through the only Google Colab, you only have to run the second one. Okay, so just mind that, and then you load. The second step is loading the libraries. That's fairly easy, and then load the data set. And that's only those three steps are needed. I ask that you do it right now. If you don't want to delays later, like running every cell, I'll try to do it, with you. But sometimes it takes longer for some people than others. So just a warning there. This is a question some people think they have answers to, but it's a very broad topic. It's far more than meets the eye, or that is typically discussed, this topic, what it involves. So I'm going to explain it, even though I think a lot of you might know or think you know what it means. So first thing to know about these terms, explainable AI, interpretable machine learning, is that they are the same thing. One stems from academia, another more from industry, but they're typically used interchangeably. There are some academics that are pushing to kind of divide the terms to put different meanings to them, but as far as industry professional goes, we use them interchangeably. I prefer the term interpretable machine learning, so I like to use that term. I've used it in my book and so on, but that's just a personal preference. The second thing to know is that they become increasingly more popular over the last few years, as evidenced by these Google trends. Likewise, during the same period, there has been more and more mentions of in books for both terms. However, the vast majority of these books have been either non-technical books for a business audience, books about AI ethics, or academic publication compilations of peer-reviewed research. Uh, Practitioner-oriented books like my own on the subject have been scarce all these years. In fact, my book published only 9 months ago was only the third one. Thankfully, by mid 2022, there'll be 5 more books. So, what exactly is interpretable machine learning or explainable AI? The main concepts are fairness, accountability, or transparency, or FAT. You expect a machine learning model to produce fair predictions. They must be robust and traceable back to something or someone, and you should be able to understand how they were made. There are many concerns associated to these concepts grounded in ethics. And ultimately, what we're trying to know is, can we trust the model? Trust is mission critical. So it's fair to ask, is interpretable machine learning and ethical AI the same thing? Not really, but both concepts overlap. Ethical AI, also known as responsible machine learning, encompasses much more than interpretable machine learning because it includes data and algorithmic governance aspects. These aspects include privacy regulations, data management procedures, and even modeling standards. They also uphold FAT. On the other hand, XAI is how we can implement FAT with machine learning. However, these very same tools used for ethical reasons can be used without ethical reasons in mind, simply for curiosity, and they can also be used unethically too. Next, we'll talk about what exactly is fairness. The slide is old, I didn't put, and the origin of bias. We won't get into that at the moment, I think, but I will explain fairness. There are three notions of fairness. There's treatment, process, and outcome. Um, Unless robots are interacting directly with us, only the last two of these pertain machine learning. Um, First, there's outcomes. In other words, predictions being balanced from a statistical point of view. That's what my notebook session will focus on. Then there's a question of having a fair process. Uh, Algorithmic this may mean many things, but I prefer to see no double standards. In other words, the same thing is applied to the same population or the same grouping. You can apply different rules to similar people or similar whatever it is your data set has. This is a counterfactual notion of fairness because like you want to make sure that if your neighbor and you are the same, you're getting the same conditions at the bank, or you're getting the same uh, treatment somewhere, where you do business. So fairness in practice for machine learning is often a balancing act between procedural and outcome fairness. Um, since fair outcomes seldom come from equal procedures. By creating the same procedure, you're already kind of making things unfair from a statistical point of view. So why focus on fairness? When you hear explainable AI, what comes to mind is explainability, interpretability, and that's typically where people stop. But that's just the base of the pyramid. As complicated as this may be, the base level is actually the low-hanging fruit. And the farther you go up, the harder it becomes while being less in top of mind for machine learning practitioners. Um, However, it's more important to the general public what's on top. In fact, most of the AI blunders involve issues of privacy and fairness. They're typically up here, and to a certain extent, the robustness. Um, like end users are not like quarreling over, oh, I don't know exactly how this works. The reason they bother to wonder why the model doesn't work is because they find it unfair or inconsistent or that it kind of in some fundamental way infringes on their privacy. So what I suggest is we begin on the top of the pyramid where unfairness is manifested as bias in the data and corresponding predictions. Uh, that way we're not skipping any steps because the top layer depends on the other two. You know, just like a pyramid does, the top layer does not really hold itself without everything underneath. In other words, you can't really make sure that a model's fair if you don't make sure that there's accountability and transparency. So I might skip this, but basically bias is in the data, what I'm trying to say. In supervised learning, we derive meaning and predictions from a model that is supposed to be represent the truth. We make a big assumption that this data accurately depicts the truth. The most fundamental problem we're about is bad data, typically data entry errors, random if we're lucky. However, there's also biases associated to bad data we should control for, and anomaly detection methods and comparing with external data sets for issues in distribution can help correct these issues. As for the truth, which is like the source of everything, we have a whole host of issues. First, we have the ugly truths, all the prejudices and systemic biases that exist in the world, and our data is merely depicting. It's not a problem with the data. It's a problem with the data generation process, or a problem, even further than that with the truth. Um, we can make sure that our models mitigate them. Our models don't have to reflect the truth that exists. Our models can, after all, reflect the truth that we want. Uh, we can also have fake truths, which are the many ways models can be purposely tricked, and truths that change over time. And all of these issues aggregate data issues. Lastly, we have our own biases with our models. Chief among them is an observer bias, where we blind ourselves to what we assume or want to be true. Not all these biases lead to unfair outcomes or procedures, but they can. Having a data-driven approach to machine learning, as Andrew Ang has been promoting, can go a long way to mitigating them. You have to make sure that you see this part, that you're really scrutinizing everything here before you get to this part. We don't go a deep dive in this session about all this part, but this is certainly very, very important. So the solution, is don't blame a complex black model for bias. Obviously, the model, whether black box or not, can amplify bias that already exists in the data. So the process of detecting and mitigating bias, it starts at the source, but you don't stop there. You have to perform it on the data and throughout the machine learning workflow on every single step to ensure that whatever remains is not amplified. So I'm going to stop at that note. I'm not going to continue through more slides, but and I'm going to go through the notebook right now. So I'm going to share a different screen right now. That's okay. Yeah. Okay. So this is the notebook I had discussed with you guys earlier. So there, it can be seen also here. If you go to the repo, and you can find it right here, adult income underscore DeFi. It's the very same. I highly recommend going to the collab, which, as I said, this is going to search.ai slash DeFi 2021, and we'll take you right there. Okay. We will install several tools. That's the first thing we do. Skip this one, as I said. So while this loads, I'm going to show you what this means. This is AI Fairness 360. It's a popular library for fairness metrics and mitigating bias. Um, it's by no means the only one. It's done by IPM, and in addition to AI Fairness, there's this one as well by Carnegie Mellon University and the What If tool by Google. There's also Fair Learn. I believe this is by Microsoft. Um, in addition to that, there's a few that are all done specifically for NLP. So this is the word embeddings fairness evaluation framework. This is if you want to mitigate bias in word embeddings. And there's also Allen NLP also has something for word embeddings, and there's responsibly.ai does the same. Lesser known tools are Scikit Fairness and Scikit Lego. This is by Lego Group. Interesting, they're in the AI space as well. So these are already loaded. Loaded installed. So now I'm going to load the libraries. I told you this could take a little bit. So we're going to load all those libraries. So completed. Now we're going to load the data set. So we're going to inspect the first rows for X. X is the features. If you worked with machine learning before, X is the features, Y is the labels. So this automatically loads them separately. You don't have to separate them yourself. So here you see all the features for this data set. And this is a very popular data set called the adult data set, and it's a census data set. And the whole point of it is to how can we predict the income of someone. So if they have this label, if they make over 50,000, and they have this one if they make less. So it can show how biased things are, and we'll see exactly how. So let's first obviously check something that you probably imagine that those making more than 50,000 are a minority. So therefore, if I take the length of those that make over 50,000 over the total length in the labels, I'll get, yeah, it's more or less a quarter that make over that amount. But this gives you a false expectation that it's distributed equally amongst genders, amongst races, and so on, and that's not necessarily the case. So we create a simple data frame here where we just pair these things together, sex and annual income side by side, and then we just do a grouping, and divide. So we group by sex annual income first and get the size of each, which will give you a certain amount, of distribution by sex and annual income. What it does is count things, count male under 50,000 and male over 50,000 and female over 50,000 and under 50,000. And just as it does here, it does a count. But then, so we get a percentage, we then group by only sex. So we're getting the percentage of the total by sex. So here we'll get female under 50,000 and female over 50,000. We see how it's distributed amongst females only. So you get that nearly 89% of females are under 50,000 and only about 11% make more. On the other hand, males, you see a lot higher percentage makes over 50,000 for males. So that's definitely indicative of that distribution reflects a real truth out there, but it might cause the model to think that females are, you know, far less likely to make 50,000. And all calls to what is this model for? Because if we're going to make a model that predicts, uh, you know, who is making a higher income to qualify them for a loan or uh, something like that, that can be very unfair. If it's used entirely for academic purposes, just simply for curiosity to figure out, what's the reality, then it's a different exercise. So that's one way of doing it. Another one is to, just visualize it as a plot. So there's this plot, there's this other tool called the XAI, which I didn't look over here. And it's it has a very rudimentary set of tools for dealing with bias in data sets. One of them is to balance a data set. So that's a tool that is very, I would say, overused. When you have imbalance in machine learning, the go-to tool is, oh, let's balance things out. So what that looks like is say, okay, well, we have this line here. We're going to make sure that everything matches. So there's an equal amount of females, and males that make under 50,000, and there's a proportional amount. So both have a 25% chance of making over 50,000. And that only partially solves a problem like this. And in a way to get there, sometimes you have to do something called upsampling. Forgive me. And upsampling, it can be very damaging, because you're basically taking each one of these observations here and you're multiplying it times a certain amount. So you're going to get duplicates. Um, that is not a great idea. It's better to go downsampling, but if you go downsampling, you're actually reducing the amount of data you have. So what that would look like is you say, okay, if this is a 25% of this, then I only need 4 times that for females. And if this is, in this case, I can reduce this to a 25% instead of a 31%. And there you go. I have something that is balanced. Yet we're not going to do that, just to reiterate, we're not going to do that. So the next thing we're going to do is some data preparation steps. We're going to create a data frame with both the X and the Y, and we'll need that later just for presentation purposes, but we won't use that in the training of any models or anything like that. Then we're going to encode the indexes of X and Y, because right now they're in text form and we need them categorically encoded. We're going to define a seed for reproducibility. And then we're going to test, train, split the data, which means we're going to take the X and the Y and we're going to split it into train and test for each. We're going to one-hot encode the features, but before we do that, we're going to create, just as we created this all underscore df with all both test and train in the same, and X and Y, we're going to separate that all into train and test in accordance to the way this was split. So what this does is get the indexes, just the indexes of all the training. All the examples are in the train data set, and we're going to make sure that we have train underscore df with all of them and test that has all of them. The difference between this and this is that this simply has both the X and the Y. In other words, the features and the labels. Then we're going to one-hot encode. This takes care of it. It does it automatically. Um, so mind you, I'm not going to focus too much on this part of data preparation. These are pretty important steps. I suspect probably a lot of you have already done these sort of things before, so I'm not going to explain every line of code here because I want to focus on interpretation and mitigating bias and all that. But you can always go back and check the code and see exactly what it's doing if you don't understand. So the next thing we're going to do is quantize data set bias because as I explained in the presentation, data already comes with bias. In this case, the bias comes in the form that according to the data, it's far less likely to have a higher income if you're a female than a male. So this is what these will demonstrate, these two different metrics. And it's easy to generate these metrics. These metrics are part of the AI fairness library. And all you need to uh, put in them to get it is two things. Well, first, the label, and then what is the name of the protected attribute. I could change this to a different attribute. Um, in this case, I could put race as well if I wanted to, because race is one of them. So I'll explain what these metrics mean now. Uh, there's on one hand the statistical parity difference, which another term for it is the mean difference. It's the difference between the main probability of favorable outcomes between underprivileged and privileged groups. In this case, underprivileged is female, privileged is male. So a negative number is bad for the underprivileged group, and a positive number is better for the underprivileged group. But in this case, a number closer to zero is always preferable because it means there's no difference. In other words, there's parity between the privileged and underprivileged group. It's computed with this formula, so it's as you said, it's as I said, it's just a difference between one and another. So you have the probability that y equals f. Well, in this case, f is the value of the favorable class, so the favorable class is 1. So the probability that y is 1 when you're underprivileged for the underprivileged group minus the probability that y is 1 for the privileged group. So that's the difference there. Disparate impact is incredibly similar than statistical parity difference. It's just the ratio of one over another. So what you're trying to see there is how, proportionally, how less likely females are to have a higher income than male. And you see that they're 36% less likely. No, 36% of males in that sense. So it's proportionally, it's actually like 60 something percent less likely. In any case, the point here, since it's a ratio, it's that it has to be closer to 1. And as you can see here, it's far from 1. So how can we make this better? Of course, there's a fundamental problem with the data, which has to do with representation. As I explained earlier, there's definitely something we can do with representation to fix that. I'm not covering that in this session, but whatever we do improve is what we can improve uh, without messing around with the distribution of this. There is something that can be done there, and it's in a way creating synthetic data or something of that effect. So now we're going to move on to the modeling. The first thing I'm going to ask you to run is this. There's a lot of code here. What this code does is simply for evaluation. So I'm just going to ask you to run it. You can review it in your own time later. but it's one of the functions evaluates any classification model, and the other function, what it does is compares confusion matrices. So I'm just going to run that like that. Then we're going to train two models. First, a logistic regression model, and then a cat boost model. So here we see the level of accuracy for test and train. There's not significant overfitting at all. It has a good precision, and recall is okay. As you see, all the metrics look kind of healthy. And when you go into the confusion matrix, which I always recommend that you do, if you look at the top right corner, you look at the false positives. If you took a look at the bottom left corner, you look at the false negatives. You see it's far more likely to have a false negative than a false positive. For this particular problem, you have to think of what is the worst of these two, the lesser of both evils. If you're going to misclassify which one is preferable is always a good question. It always depends on what you're trying to achieve with this model. Some of the reasoning might be business wise, like for instance, if you're trying to predict who has the higher outcome, the higher income, so because you're sending people catalogs for some very expensive, I don't know, furniture or I, I don't know, real estate. And so you want to make sure they can afford it. So you're going to send them these catalogs. These catalogs have a price. So you have to factor in how much the shipping would cost. So what's the harm in sending, if you're looking at the false positives, what's the harm of sending people that can't afford what you're selling a bunch of catalogs? There's no harm to them. There's harm to the business because you're losing out here. But on the other hand, with the false negatives, what you're getting is you're losing potential customers, people you could possibly send catalogs to, and they could have possibly afforded your things. You're losing a substantial amount of it. So in that scenario, from a business standpoint, you rather have false positives than false negatives. You rather send a bunch of people that can afford your what you're selling, your catalogs, than missing out on the opportunity of uh, of getting more customers here. So you're gonna bite the bullet in the trying to increase this number of true positives here. You're gonna try to shift this from here to here, this 10% from here to here. So that's a valid reason, right, for that particular problem. But if you look at it from a ethical point of view, there's a lot of use cases in which actually it's more harmful one or another. So if you're using this data set to predict if someone is worthy of a loan, then a false positive um, is good for it's good for your end user. It's good for the loan applicant, but it's potentially bad for the bank. You have to figure out how much, but it also you have to look in how much it discriminates people on this end. So the false negative is harmful to people because you're saying, well, you're not you're probably qualified for a loan, but you're not. Your model's predicting that they don't. So in that case, you have to be very careful with the false negatives. So the focus of the session will be looking at the false negatives, in particular to the false negative rate. So now let's go with the Caput classifier and see how it compares. So you see here, it's a lot better. All the numbers are better. It has a higher accuracy overall. there's a shorter distance between the false negatives and false positives. I discussed the balance between these. You can definitely implement something called cost-sensitive training and ensure that there's more balance there, whatever way you want it, depending on the use case. This is the reason I commented it here is because you can add this this over here. You can play around with this weight over here, and this is a form of class weighting. And class weighting ensures that one class misclassification is penalized over another. And so, in other words, that is going to toy around with these two over here. So if you add weight, you can either shift some of this over here, you end up with a higher percentage of false positives versus false negatives, and so on. So in the absence of not knowing what this model is for, I can't tell you what would be the best solution, but it's something you can toy around with. And in the context of fairness, it's important to look to mass classifications. We're going to assume that false negatives is worse than false positives. So we're going to focus here on that, but it's always good to look at that. And in this tool in particular has a very nifty tree over here where you can look at what metric they recommend based on basically answering that question. What is more damaging, false negatives or false positives to your your underprivileged group, which in this case is females. So now we're going to visualize or detect model bias. So we're going to precisely do what we did here. We're going to take, we're going to figure out, okay, which ones of our labels are males. So we can do that by doing this. So what this returns is a, if we go here, I'm just going to show you because this can be a bit confusing. It's just an array of false, true, true, false. It's a logical array. So we can, this is a logical array that has the exact size that the labels do as the predictions. So we can do it to discriminate. It's either male or female, and we can feed that to our compare confusion matrices function that we defined earlier. So on one hand, we have the labels and the predictions for male, and we have the labels and the predictions for female. It, as you see here, it's exactly the same, except here it says not male. So it's just reversing all the true and falses here. So therefore it's ending up with female. That's all. So we can compare them, and this is what we find. This is all relative because we haven't changed the distribution. If we would have, as I said earlier, changed, made sure that females were 25% and males were 25% likely to have a lower income, then we would expect similar numbers on this diagonal. But since we didn't do that, it's all relative to what these numbers on this diagonal are compared to this diagonal, which is the misclassifications. So what we're trying to figure out here is the false negative rate. And if you recall, the false negative rate is the false negative over the false negatives plus the true positives. So it's basically this quadrant over the sum of these two. So we're trying to predict what percentage is this over the sum of these two and so forth. So we find that females have a false negative rate of 52.9% and males have a false negative rate of 41.1, which in this case is lower is better. So when we look at the ratio, we figure out females are 29% more likely to have false negatives. And this is for the linear regression model, by the way. Now we can do it for the cat boost model and see how it compares. We see it's significantly lower. False negatives are lower as a whole with the cat boost model. So the model, even though it performs only slightly better than the linear regression model, it's significantly better in the amount of fairness. Um, so there's another way of quantifying it, and it falls in line with what we did before because it's exactly the same function. So we have the statistical parity difference and the disparate impact. And this is what we have for logistic regression. As you can see, it's worse. Is it worse? 18, minus 18 and 26. Let me see how it was originally. Yeah, yeah, I think so. It can be worse. So and that's what you would expect with a model, because a model can make these things worse than they are in the data. You can tell that this impact is worse than it was with the data set because you would expect a higher number here. It was 36 originally, now it's 33. So, and this is expected, as explained earlier, models tend to amplify data set biases. So now we're going to go to the heart of this entire session, which is how do we fix it? How do we mitigate bias? So there isn't a lot of time to go through all the many, many methods that can be used for this. There's, you know, at least a few dozen that exist to mitigate bias. Most of them are in pre-processing or in processing, which I'll explain what they are. But there's three levels. You can deal with it on three levels. One pertains to the data, and that's pre-processing. The second pertains to the model and its training, and that's the in processing. And the third pertains to the predictions. In other words, you are basically changing the predictions, and that's the third, and that's called post processing. So that's very intuitive, and that it makes completely a lot of sense, and I suggest you mix and match. You work on every level. So as explained here, there are interventions to detect and remove bias from the training data before training the model. So one of the most popular one is called reweighting. So much like class weights are applied to each class, sample weights are applied to each observation or sample. I would say many, not only many, but most regressors and classifiers support sample weights. That's something people aren't aware about, but in the fit, you go, model dot fit, you got X train and Y train, and then there's a lesser known parameter called sample weight, and you go sample weight equals, and that's they most support it. So even though technically reweighting doesn't touch the data, the solution is applied to the model. It's a pre-processing step because we detect the bias in the data. So it detects the bias in the data, and the pre-processing step is actually the calibration of that. So here we're going to do a calibration step where we're going to do it through logistic regression and via grid search and then evaluate. The reason we do it is because it could take longer to do with CapBoost. CapBoost is obviously our best, model, but we're going to do it with logistic regression because this is fairly quick in logistic regression. So now we're going to do again the statistical parity difference. As you can see, it took an impact in accuracy. That's something you're going to find with bias mitigation methods, is that they do impact predictive performance. So there is a trade-off there. You want to make things fair, your model is not going to perform that well. But on the other hand, you have to think, how unfair is that the model is performing less? So it's also a question of going back to the confusion matrix and seeing, you know, if I shave off some of this over here, does it make sense? The trade-off I'm doing between the two groups, you know, so it's kind of a balancing act. So let's run the statistical parity difference, and you can see there's been a great improvement. You know, it pretty much almost halved the statistical parity difference. And this predict impact, it increased it by a great amount. It went from, what was it, 36 to 54. So it's not quite at one, you know, it's not perfect. To get it at one, you have to do some other things as well. It might not ever get one. That's the thing, without impacting accuracy greatly. And that's why we do a calibration step, because we could definitely reweight everything so that we got better numbers, but then we impact accuracy greatly. So there's a trade-off there, as I explained. So to examine how it works, I'm gonna take this the reweighter that I established here, which is this one. I'm gonna extract. I'm gonna do a fit all over again with this data just to get the weights back. So it's gonna return the sample weight. So I go like that, and then I can look at the sample weight. So as you can see, they all vary. And this sample weight has the size, it has the length of the training data set. So if the training data set has 30,000 samples or observations, you'll end up with this array of 30,000, one applied to each one. What you have to realize is that you would think that adding weights to observations would greatly impact predictive performance. However, this method was designed to maintain balance. In an unweighted data set, like when you run the machine learning model without setting the sample weights, by default, every observation is going to have a weight of 1. So it's all going to be 1, 1, 1, 1, 1, 1. And so therefore, the average of all those ones is 1. While reweighting changes the weights for all observations, the mean is still approximately 1. So it's not really changing anything as long as the mean is 1. So that's why it works. So now we're going to move on to in-processing method. And the in-processing method we're going to use is called adversarial devising. I'm going to reiterate what in-processing means. In-processing means we're mitigating bias during the model training. And so it's also highly dependent on the model and tend to not be model agnostic for that reason. Like pre-processing, post-processing, because pre-processing you're just changing things in the data. Post-processing, you're changing things in the labels or the scores, in other words, the predictions of the model. And so they're not connected to the model in that sense. But in processing, it's intimately connected to the model, and so it's therefore not model agnostic. So it's gonna we could do some that are specific to cap boost or to logistic regression, or in this case, adversarial devising is actually neural networks. So what it does, it leverages two opposing actors. You have a predictor and an adversary, pretty much like a GAN would work. We maximize the predictor's ability to predict the target while minimizing the adversary's ability to predict the predictive feature. So we're penalizing the model if it predicts because it's based on a protective feature. So it increasingly increases the quality of odds between privileged and underprivileged group by taking that adversarial approach. So it's going to create a TensorFlow session. So we also have to make sure we close the session at the end of it, but we're also going to evaluate the class here the same way we've done before, the classification model, I mean. Uh, so see, the accuracy, it keeps dropping, but you see there's minimal overfitting. However, if the accuracy dropping even further is indicative of better fairness results, indeed, we got it. We're at 59%. I said that was the ratio, so it's okay to call it a percentage. So this one is 54 and minus 10. This one is minus 9.7 and 59. So it's improved by just this approach. And indeed, we can combine this with also a pre-processing method, not this method, because we can apply reweighting in combination with this one, but we can certainly look into other pre-processing methods and use them accordingly. So the next one is this post-processing method. And as I explained, post-processing methods aim to detect and correct fairness directly in outcomes. So what adjustments will make depend on what metrics matter most to the problem. It's very tricky on this end to do that because especially with the classification in particular, there's things that, there's the idea of should we change the scores? In other words, should we change the probabilities or should we change the labels? And changing the labels, it's actually fairly simple. It's just a question of saying, okay, usually you say, well, you get a 1 as a label if it's over 50%, and you get a 0 if it's under 50%. That's typically how it goes. But we could say, well, if it's a female, we're gonna lower the bar, we're gonna drop it to 40%. If it's a male, we're gonna increase it to 70. Or maybe we don't have to drop it for one and we just have to increase it for the other. But just by doing that, we're gonna actually change the labels, and therefore we're gonna do some we're gonna make things achieves a certain parity. And that's one kind of post-processing. The kind we're gonna try right now, we're not changing the labels. We're modifying the probability estimates so they're on average equal. So this is called calibration. However, these constraints cannot be satisfied for false positives and false negatives concurrently. So you're either focusing on one thing or another. And so therefore it's advantageous in cases where recall is far more important than precision, or vice versa. So in this case, as I explained before, our focus is the false negative rate. That's what we're trying to achieve parity with, the false negative rate. We don't care that much of the false positive rate in this particular case. But if we were, this would be very simple. We just go like this, and that's it. So first, we're going to use the calibrated equalized odds. We're going to define it. And you define it like this. You first say what is the protected attribute, what is the cost constraint, and then you put the random seed. I haven't been explaining throughout this notebook about these, but it's always important to be consistent and to make sure you have the same number defined. I think I defined 42, so you have 42, 42, 42 throughout. We're gonna use this CapBoost classifier and this post-processing um, uh, cross validation, and we're gonna use this post processor that I defined here, and then we just go like this. So as you see here, it has better accuracy than the previous one. Um, if I may say so, something to note here, this performs worse, and you can check if I don't do this. So a trick I'm doing here, it's not really a trick, or I'm not really cheating. I'm not just using one method, I'm using two. So it uses post-processing with the calibrated equalized odds on the way out, but it also uses sample weights on the way in. So if you remove this, you'll get worse results. Just FYI, and that's a good thing. We could use all three methods. We could chain them together in such a way where we're using in processing, post processing, pre processing all together if we wanted to. Here I'm just using two of them, and as you see, you have minimal overfitting. You have good test accuracy. Everything is very healthy. And then when we look at this, the disparate impact is not nearly as high as it was up here. But that's all relative. And then we have the statistical parity is still way better than it was originally. So this is especially visible with the confusion matrices. You look at here, you see we're getting good FNRs. So it's focusing on FNR. This is what this is doing. Like we're getting worse numbers when measuring disparate impact and statistical parity difference. But since this method is precisely focusing on FNR, it's minimizing the false negative rate. And indeed it did. It did a very good job. This is the lowest we've ever had it at 1.07. So this is as close as it can probably get without resorting to other methods. So lastly, before I go, I'm gonna just show you one plot, and this is the precision recall plot. And it's important to also look at it in these terms. We've been looking at the confusion matrices, and this is a good way to look at it. And originally we were also looking at the ROC plot, but actually for imbalanced data sets, the best approach is looking at the PR plot rather than the because this gives you a false sense of a false sense of what your prediction performance is in the light that it's actually an imbalanced data set. The PR curve is a lot better for that. So another thing you can do with PR, as you can with ROC, is uh, do one curve for one class and do another for another. So you can compare them side by side, and if they're close together, then it means that there's some parity there. If they're separated, it means you know there's some work to be done. So here we're going to just iterate through both protected classes. I know we haven't been focusing on race, but there is, in fairness, a complication when you have several dimensions you're trying to, or several protected classes, protected groups, or protected attributes. Actually, attributes is the word that you're trying to correct. So if you have race and sex, you have a cross section, a cross tab of different groups that you're trying to protect. And it's complicated because some biases are amplified on a lower level. So non-white females might be even more discriminated than females in general, and so on. So it keeps becoming worse and worse the more groups you have. So once you're putting like race, sex, and I don't know, sexual orientation, then you have uh, on three levels it compounding that level of bias. And because of Simpson's paradox, which I'm not explaining right here, but please search it. It can become even more complicated because it becomes less intuitive. You would think that one group that is discriminated as whole and another group is discriminated as whole. The Venn diagram between both, they're going to be even more discriminated. But that's not always the case. There's a lot of things going on, a lot of that makes it possible for groups that are as a whole discriminated have subgroups within it that aren't. So I'm not going to get too into that. It's a fascinating topic, but I'm just going to show this graph over here. This is the before and after. This is for race, and this is for males and females. And you see, it's a lot bigger for race than it is for females. I focused for females for gender. I focused on gender right now because I just wanted to have a simple use case for this. But they could have been equally important, and we could have worked on both. But by actually minimizing in one, we actually improved it in the other, as you see here. So this one is nearly zero, the difference between one another, exactly as you can figure. This is the effect of focusing on the false negative rates. This is almost the same on this side. And so here you see there's still a gap, but it's actually less than it was before, which is good. But there's some fairness metrics that we can tweak, that we can try to improve, that focus on these cross sections. So ahead, I'm not going to get into it right now, but it's definitely something you can look into by looking at these tutorials for a Fairness 360, or for this tool over here that probably have the most available in terms of working with this sort of problem. So that's it. I'm done with with this notebooks and therefore the presentation. Thank you for joining, and I'm open to any questions.
Yeah, thank you, sir. So, for such an insightful session. I think there are a couple of doubts from the learners, which we can pick. So one of the learners asked this question that generally, we see that explainable AI is a bit less accurate. So how can we sort of balance the accuracy and interpretability of our models?
Explainable AI is less accurate?
Yes.
Is that what you said?
Yeah.
You mean in the fidelity of the explanations?
Right. So in terms of accuracy, how can we balance both things out?
Okay, I see. They're talking about the trade-off between explainability and okay. Yeah, like that's something. Often you're told, okay, well, you have to make a hard trade-off. In other words, you have to go for the most simple model, and that's the solution. Okay, yeah, complexity is a big issue. Complexity in machine learning, because complexity is the source of a lot of our problems, from overfitting to bias to lack of compressibility. There's a lot of things that come from that. So you don't necessarily have to tackle complexity problem by choosing a less complex model, because data by itself is complex. You're not necessarily going to create good models by saying, okay, well, I'm going to make everything but linear regression.
Right.
Linear regression might be a great solution for some use cases, but terrible for others. So you just have to choose the model that is complex enough for your particular problem. Just complex enough, not more. Don't go for a neural network when your model doesn't warrant it. your model, your use case doesn't warrant it. What I'm saying is it's not necessarily a question of the model is the one that you should tackle. I think that's what the listener was trying to say
Right.
by saying, okay, the trade-off, but I think the complexity can be tackled on other levels. The complexity can be tackled on feature selection. It can be tackled on regularization. It can be improved by actually putting guardrails. Something that I discuss in my book is different kinds of guardrails. One is doing specific kinds of feature engineering
Mhm.
that reduce some of the complexity of the data. So some of that could be binning things rather than using continuous values. There's many ways of doing things that will actually reduce complexity from a feature engineering standpoint. There's also the other one is constraints. A lot of people don't know they can put monotonic constraints on certain kinds of models,
Mhm.
and so that ensures that there's always an intuitive direction between a feature and the outcome. So you could say, well, people that tend to be late on their payments
Mhm.
will default on their loan. So you can say, okay, if people have this history
Mhm.
that they're constantly late on their payments, then that should be immediately tied with their ability to be getting a loan or not.
Right.
That seems like a fair thing to do, maybe. And if you do that, you can ensure that there's like this intuitive rule that you have in your model that one thing goes after another. You know, another one is to say, well, people that get good grades are should be rewarded with being admitted to the best universities. So you could say so there's a consistency there. You say, okay, the higher the grades, the more likely to get into this university, right?
Right.
So that could be a way of tackling that, and that's a procedural kind of fairness, and you can do that and by enforcing these rules. And these rules actually reduce complexity because the models no longer find gaps,
Right.
like
Right.
exceptions. And so, yeah, it's a long answer, but
Got it. Got it.
it's a
Yeah.
complicated subject.
Yeah, I think like it gave a really good context to the learner as well as to me as well. I think you explained it really well. I think like there are two more questions. One, like initially I think like in the slides you mentioned that the first source of bias is the data that we take, right?
Hmm.
So is there any way like we can tackle that particular bias before even start fitting into our models?
Yeah. Um, there's a topic that we don't discuss enough in machine learning, but like practitioners, uh, we spend awful amount of time dealing
Mhm.
with it, and it's data cleaning. Uh, Data cleaning
Mhm.
can fix a lot of these issues.
Mhm.
There's obviously a philosophical problem, which is, like we think that the data is the ground truth. It's like we shouldn't mess with some things. Yeah, we should remove errors and so forth, but should we balance things in such a way where we're actually addressing societal problems? Should we be you know take out information that is useful because
Mhm.
it's biased? Should we do a lot of things like that? And
Mhm.
I say absolutely yes. I
Mhm.
mean, I think there's a moral imperative to do that. The question is, it can't be completely unguided and disorganized process. We have to,
Mhm.
sit down with stakeholders and figure out, what are the things we're trying to achieve.
Right, right.
And the thing is, when it comes to fairness, we're not just trying to achieve a good outcome for a business, but we're trying to achieve a good outcome for other stakeholders as well. So we have to measure, to what extent do we want to, say we're going back to the banking example. How much do we want to help the bank increase its profits while also not discriminating against, uh, people that have already previously been discriminated on.
Right.
Because and you might end up, even though the model might tell us that the performance is lower, you might end up with better performance. Because that's the tricky thing that machine learning can't really tell us, give us the solution to this problem, because there's a tricky thing to that, which is like the models we produce change the future, right?
Right.
And as they change the future, they can change the future for the worse. So it becomes like a self-fulfilling prophecy. So if you predicted a certain group to not be able to pay back their loans, maybe they don't, because we gave them very bad terms, right? So by giving them very bad terms, they became more likely to not pay their loans. So
Right.
that is that we have to be conscious of that part of what we do. So how do we correct that? What I say is we don't have to predict the future based on the past if it's biased. We can tweak things in such a way carefully. It's good to also experiment through other means. And that's why I said machine learning doesn't have all the answers. By those other means, I mean A/B testing, causal inference, all kinds of experimentation methods that
Right.
have existed for a long time in statistics. We can use that to kind of gauge our efforts and figure out, okay, if we do this, this is what we expect. And therefore, we can change this in our training data so that we get these results. That way, we're purposely trying to change the future. We're not just trying to predict the future, we're trying to change it.
Right.
And as someone, like Adam Kay, um, he's the inventor of Atari. I don't know if you remember Atari, but it once was like a fierce competitor of Nintendo. He said, Alan Kay it is, he said, the best way to predict the future is to change it. So if we make sure that our loss functions and our optimization problem is aligning with something that is plausible and probable and grounded in our experiments, we can achieve that outcome. But the question there is we have to change the training data to get there. We have to change it significantly. And that means removing bias. That means carefully, like, deciding what features to include and not just leaving it up to let's get the best predictive performance based on our holdout data set, because our holdout data set is also biased.
Right. Right. Yeah. Yeah. Thanks, Serge, for the wonderful answer. I think, one last question, which I personally like to ask for all the learners. Any key piece of advice you'd like to share, for all the AI enthusiasts who have joined us?
Okay. Yeah, like the biggest advice I have, I mean, is first ask why, then ask how. I mean, why is more important than how. Like, a lot of machine learning has been obsessed with how. Everybody wants a simple recipe for, using TensorFlow or whatever and cookie cutter stuff. And that's all great. We all need recipes, but we also need to understand why we're doing things, why we're getting the results we're getting, and why it matters to change those results and on what levels. So by that I mean, I think there needs to be a reckoning, and I mentioned in the presentation how Andrew Ann has been discussing this at length, data-centric AI, and I totally agree with his vision that we have to get back to the data. We can talk on and on how we need more data quantity, but quality is at the core of everything, and not only quality but qualities. We have to understand data better so we can make better models. And we have to think, it shouldn't be brute force. It doesn't have to be an arms race on who can make trillion parameter models. You know, it's all a question of why do we need trillion parameter models if 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 us humans, we don't use all these parameters to deal with things with language and so forth, and yet we manage, we manage with a lot less resources. So it's and that speaks to how data is organized and how things at their core, their probabilities and these intersect, and of course models. There's a bunch of things that of data points that models don't have because the data training doesn't have. So we have to think of these things. We can't, and we have to go beyond associational thinking and go into causal thinking. And to do that leap, we have to ask the question why, because why is the key. Why is the key to everything, I think. I guess I'm getting a lot philosophical there, but
True that, true that. I think like that's a really, really strong and important advice for all the AI enthusiasts out there. I think this is the perfect note to even sort of end the session. Once again, thank you everyone who have joined, and we hope you really enjoyed the session. And many thanks to Serg for taking out this time and taking this wonderful session. Bye bye, guys. Have a good day.
Thank you very much.